We're asked to find the critical points in linearization of the given system of differential equations. We have x prime equals x plus y squared and y prime equals x. Looking at our notes on the right, the critical points are where the derivative of the xy vector is equal to the 0 vector. In our case, notice f of x comma y is equal to x plus y squared, and g of x comma y is equal to x. In other words, we need to find the points where both f and g are equal to 0. This indicates we need to solve the system x plus y squared equals 0 and x equals 0. Because we know x equals 0, we can substitute 0 for x in the first equation, which gives us the equation y plus y squared equals 0, which we can solve by factoring. This gives us y equals 0 or y equals negative 1. This indicates we have two critical points, 0, 0 and 0, negative 1. And now we need to find the linearization at both critical points. Looking at our notes on the right again, number 1, we change the variables to u, v, so that u, v equals the point 0, 0 corresponds to each critical point x sub 0, y sub 0. This indicates we let u equal x minus x sub 0 and v equals y minus y sub 0 for each critical point. Let's start with the critical point 0, 0, and therefore we have u equals x and v equals y. Step 2, we find the derivatives using the Jacobian matrix shown below, where again f of x comma y is equal to x plus y squared, and g of x comma y equals x. For the first row of the 2 by 2 matrix, we have the partial of f with respect to x, which indicates we differentiate f with respect to x, treating y as a constant, which gives us 1. For the second entry, we have the partial of f with respect to y, which indicates we differentiate with respect to y, treating x as a constant, which gives us 1 plus 2y. And then for the second row, we use g of x comma y. The partial of g with respect to x is equal to 1. The partial of g with respect to y is equal to 0. And now we evaluate the Jacobian matrix at the critical point 0, 0, which gives us the 2 by 2 Jacobian 1, 1, 1, 0. And now we can find the linearization at the critical point 0, 0. The derivative of the uv vector is equal to the 2 by 2 Jacobian at 0, 0 times the uv vector. This indicates with u equal x and v equals y, the linearization is u prime equals u plus v, and v prime equals u. And now we need to go through the same process for the critical point 0, negative 1. Let's do this on the next slide. For the critical point 0, negative 1, x sub 0 equals 0, and y sub 0 equals negative 1, giving us u equals x and v equals y plus 1. We've already performed step 2 from the previous critical point. We know the Jacobian has entries 1, 1 plus 2y, 1, and 0, but now we need to evaluate this at the critical point 0, negative 1, which now gives us the 2 by 2 Jacobian with entries 1, negative 1, 1, 0. For the linearization at 0, negative 1, we have the derivative of the uv vector equals the 2 by 2 Jacobian at 0, negative 1 times the uv vector. This indicates with u equal x and v equal y plus 1, the linearization is u prime equals u minus v, and v prime equals u. Before we go, let's compare the vector field given by the original system of differential equations with the linearization at the two critical points. On the left, we have the vector field from the given system, and we have the two critical points in orange and blue. In the middle, we have the linearization of the orange critical point. On the right, we have the linearization of the blue critical point. Remember, for the linearization, the critical point always ends up at the origin. If we compare the behavior of the original vector field to the linearizations around the critical points, we can see the linearization is a very good approximation of the given vector field as long as we're near the critical points. I hope you found this helpful.